In 28 through 42, use mathematical induction to verify the correctness of the formula you obtained in the referenced exercise. Number 29 says exercise 4, and here we have exercise 4, but we also have the solution for exercise 4. Now, we didn't actually do exercise 4 in a previous video, so I'm just going to work off of the solution that I found, and we're going to use mathematical induction to verify the correctness of this formula. Now, this is going to be our predicate P of k. Now, normally I have P of n. This is going to be a little confusing because now I'm using k. That's my fault, but the idea is still the same. The base case is going to correspond to when k equals 0. P of 0 is the statement that b sub 0 equals 1 over 0 plus 1. We want to show that this is true. So we're going to start with b sub 0 on the left-hand side, which we're given is 1, according to the recursive definition. But we can also evaluate the right-hand side of this equation. 1 over 0 plus 1 is also 1. And so P of 0 is true. Now let's move on to the inductive step. Let m be an arbitrary fixed integer with m greater than or equal to 0, and assume P of m is true. I'm using m since I technically already used k, even though k is like a local variable in the definition of P of k. I'm going to try to be coherent and separate letters here in different sections. Now, let's identify what the inductive hypothesis P of m is. P of m is the statement P of k, but instead of k, we have m. So we're given that b sub m equals 1 over m plus 1. We want to show that b sub m plus 1 equals 1 over m plus 1 plus 1, which is the same thing as 1 over m plus 2. Now, the way we're going to prove this is we're going to take the left-hand side and do some stuff to it using the recursive definition. Now, m is greater than or equal to 0, which means if we add 1 to both sides, this means m plus 1 is greater than or equal to 1, which is relevant because we need to know that the integer that we're plugging into the recursive definition is greater than or equal to 1, which it is. So that means we can apply this recursive definition, which says each term is equal to the previous term divided by 1 plus the previous term. So that means that b sub m plus 1 is equal to the previous term, b sub m, over the previous term, b sub m plus 1. So that's according to the recursive definition. Now we can apply the inductive hypothesis because we know what b sub m is. So let's plug in 1 over m plus 1 into these b sub m's here. Now, since we use the inductive hypothesis, we need to tell the reader that we're using the inductive hypothesis. So I'll put by the inductive hypothesis here. And we can simplify this fraction by multiplying the numerator and the denominator by m plus 1 to get 1 over 1 plus 1 times m plus 1, which is just 1 over m plus 2. And that's what we wanted to show. We wanted to show that b sub m plus 1 equals 1 over m plus 2. And that means that P of m plus 1 is true. And that means that P of k is true for all integers k greater than or equal to 0 by mathematical induction. Thanks, everyone, and I'll see you in the next video.